chi-square test. And I showed you a particular example where we looked at the goodness of fit test. Goodness of fit test, where we compare observed data with expected data. There are other chi-square tests, and I really want you to find some resources. There are loads and loads of resources on YouTube that discuss chi-square tests. Very often you will find that these chi-square tests are related to these contingency tables. So that would be a 2-by-2 table. And for example, a very classic thing would be, say, Mendelian genetics, or where you have, say, seed types, yellow and green and round and wrinkly seeds and things like that. It's a Punnett square, exactly. And you have some numbers, say 30, 40, 110, and 25 or so. And you've done that in your genetics module, haven't you? Yeah? And you also then have a sort of certain set of ideas. So you might have a 1 to 2 to 2 to 1 split. And there are lots of videos out there that explain how you deal with something like that. From that, you can then, for example, calculate expected numbers. So you say maybe here I would expect 40, here I expect 35. I just make something up. Here you would expect 115, 35, something like that. And then you can calculate with a chi-square test, with this graph pad, quick calcs, online calculator, are the expected and the observed numbers, are they in line with each other, or is there something else going on? And I am not going to show you exactly how you do it, because, as I said, there are lots of videos on YouTube about exactly this. But I expect you to know that. And I expect you to know that definitely end of May. Why end of May? It is the summer exams. And a little bird told me that this knowledge might be very useful for you guys. Yeah? Chi-square. Now what I want to do with you today is something else, and that is called correlation. And I think I posted this beautiful video of the dancers, which I understand is not everybody's thing. But correlation, we are dealing with correlations on a daily basis. And intuitively, we have a very good concept of correlations. Now let's translate that into, say, mathematical concepts. And that is what this session is all about. Let's say, for example, we look at, we can look at the outside temperature, and the sale of ice cream. Yeah? So, we might see, for example, if the temperature outside is 10 degrees centigrade, the sale of ice cream is pretty reduced, let's put it this way. So it would be, equivalent of maybe £3 or so. So there are always some mad people who decide to buy ice cream even when it's freezing cold. Now at 15 degrees, the sale goes up. We have maybe £25 sale. 20 degrees, yay, things go up even more. Let's say we have £110. 25 degrees, yes, we reach the £333 range. Yeah? And what you see here is we have a nice relationship. This one here, that is called our independent variable. Independent variable. That is basically what we look at, what we investigate. And this one here, this series here, this is the result, the corresponding result. So the result. And that is called the dependent variable. And traditionally, and by convention, what we do is we plot the independent variable on the x-axis and the dependent variable, our result, on the y-axis. So in our case here, we would plot the temperature here, 10, 15, 20, 25, and so on. And as the dependent variable, we would use the sale of ice cream. And what would we find is something probably like this. Yeah? Temperature in degrees centigrade. We would see something like that. And from this graph, what we can gather is a nice correlationship. And basically, well, what can we say? Yes, exactly. So, sale and temperature are directly, positively correlated with each other. There's a positive correlation. And positive correlation in this case means the hotter it is, the more we sell. Yeah? That's a positive correlation. We can also come up with something that's exactly the opposite. For example, we can ask a question, if this guy not only sells ice cream, but also hot chocolate, actually that's currently my absolute favorite, when I come home, nice hot chocolate, nice topping of cream. Yeah. And the peak of decadence, a dash of advocate, eggnog, and some some grated chocolate. Yeah. You know, you just simply forget the world. This is life. I know it's sad, but it's just good. Anyway, we look at the sale of hot chocolate. And what we see is, if it's cold, of course, the guy sells a lot of hot chocolate. But when it gets really warm, well, people buy ice cream instead of hot chocolate. So what we see here is a negative correlation. So we can have both. And then, the guy also sells gummy bears. I love Haribo. Oh, especially the white ones. And the dark red ones. But unfortunately, my daughter likes the red ones as well. So she eats all the red ones, and I get the crappy yellow ones. Life isn't fair. And what we see with the gummy bears, there's no season for gummy bears. So the gummy bears, they might be like that. Last year I made this announcement, and a student gave me, then at the end of the lecture, gave me a gummy bear that size. Oh, I love her. Absolutely love her. And I have to be gummy bears. Oh, no, I can't. No, I can't. Because I tell you why I can't. I have to mark your exams first, because otherwise it would be, seen as bribery, and I have to declare it, and I refuse to fill in 15 forms just for, a little packet. I still have to. So we have here zero correlation of the gummy bears. So, just to summarize that, what we have either a positive correlation when the line goes up. When things go up, it's always positive. Well, there was a bit of innuendo, but if things go down, it's a negative correlation, of course. And if things sort of don't do anything, it's no correlation. I want you to remember that. Now, sometimes we are not entirely sure how good is a correlation. For example, I show you a correlation. Positive or negative? Positive. Is this a good correlation? Yes? Good correlation means that they are almost all on a straight line. Yeah? So that is a strong positive correlation. What about this one? Is it positive? It's positive, it's going up, yeah? Is it strong? It's definitely not as strong as the other one. So we can probably say weak correlation, but it's still positive. It's a weak positive correlation. What about this one? Loud? Yeah, loud, Tiffany? It's a negative correlation because it goes down. But it's not terribly strong. So weak negative. So you get the idea. How do we actually determine whether it's weak or strong? We can say, okay, we eyeball it and see whether whether there are points that are off the line. But of course, in terms of statistics, this is not terribly satisfying. So what we can do is we can measure the difference between, say, this point here and this point here on the line. So we can measure the differences. We can measure the difference between this one here and this one. We can measure the difference here. We can measure the difference here. Yeah? And we can sum up all the differences. Actually, wouldn't it be better to use the squares of the differences? Because otherwise they might cancel each other out. And that is exactly what people do. This is called Pearson's correlation coefficient. So you have the Pearson's correlation coefficient, and this is usually abbreviated with R. The equation for that is rather unpleasant, and I don't want to show you to you. But what you should remember, this Pearson's correlation coefficient tells you whether it is a positive or a negative correlation, or no correlation. And it can be between -1, this would be very strong negative. So R usually is smaller or the same as -1 and can go up to +1. That would be a very strong positive correlation. Thank you. At least somebody's awake. R must be bigger and smaller than, yes, I hope now it's right. Sorry for that. So R, this correlation coefficient, is between -1 and +1. Okay? And by convention, we say if it is between 1 and, say, 0.8, or -1 and -0.8, we talk about a strong correlation. If it is between 0.5 and 0.8, it is usually considered as a weak correlation. And if it is smaller than 0.5, or in this range, 0.5 range, then it is no correlation. So if I give you an R value, R equals -0.99. What have we got? What have we got? It's a strong negative. Why do we know it's negative? Well, because we've got the negative sign here. And 0.99, that's close to 1. So it's strong. What happens if we have r equals 0.75? Is it positive or negative? It's positive, yeah, because we've got a positive sign. Now, it is smaller than this 0.8, so it is, let's call it medium strong. It's not terribly strong, because then it would be closer to 1, but it's also not close to 0.5, where we then would say it's, yeah? So it is medium strong positive. R equals 0.02. Positive or negative? Would be positive, yes. But look at the number. It's pretty close to 0, isn't it? Which actually means there's no correlation. It could be like our Haribos. Yeah? So only if it is below 0.5, below minus 0.5 and above 0.5, we would consider it as medium. So maybe I can draw that. Here's 0, here's minus 1, here's plus 1. Here's minus 0.8, 0.8, 0.5, 0.5. So this range here is no. This range here is yes, but not terribly strong. And this range here, I don't know whether you can see that, yeah, that is strong. Okay? Happy with that? So I would expect you to be able to look at the R value and tell me, is it a strong or not so strong or no positive or negative correlation? Now, unfortunately, very often you don't find R, but for some reason that is, I'm not entirely sure why people do that. They sometimes do R square. I don't know exactly why this is, why people use that, but, well, okay, fair enough, they do that. What you lose with the R square is the information whether it's positive or negative. So if I gave you an R square of 0.88, you would probably say it is a strong correlation, but you wouldn't know whether it's positive or negative. So that's why I don't like R squares. That's why I usually go for the R value. Right, how do you find this R value if you don't want to do terribly difficult correlation calculations? That storks deliver the babies. The more storks you have, the more babies you have. Very simple. Yeah? And reminds me of the story where this guy is visiting a household with 15 children and says, oh, wow, you've got a lot of children. And all of a sudden a duck comes out and he says, oh, you also have a duck. And the mom says, no, no, it's not a duck, it's the stork. He has to come so often that his legs got too short. Anyway, don't worry about that. So, what does this tell us? Storks deliver babies, very clearly. Or, do you agree with that? No. Don't destroy my world. Could there be another reason? For example? You said yes, but you don't know. Well, it could very well be that the environment after the war, the economic environment and the natural environment after the war was better. So people had more babies, the economy was getting better, and at the same time, the natural environment was getting better, so more storks came. What very often people do is they say, oh, cool, I've got a strong positive correlation here, so they must be related to each other. But it's not the case. And what I want you to do with me, chant. I want you to say with me, correlation is not causation. Correlation is not causation. Correlation is not causation. Which means, even if we have a correlation here, it does not mean that one is the effect of the other. So, coming back to the example with the ice cream, where we had the temperature and the ice cream sales. So as soon as the temperature goes up, our sales go up. It could very well be that there is a correlation, that there is a causation, that the temperature, because it gets warmer, leads to an increase in sale. So in this case, there might be a good cause, or might be an effect there. But with the storks, it's not. So you need to be very, very careful where you try to figure out what's going on here. Likewise, I could turn it around. What would happen if I turn that around and say, I measure the sale and the temperature? I probably would get a strong correlation as well. Yeah? I just change the axes. Does that imply the more ice cream I sell, the hotter it gets? No. So you need to be very, very careful with these statements. And you need to be really careful with trend lines. Make sure that you really understand what these data tell us. Is there a correlation? Or is there another effect that is possible, that we can possibly explain for the effect that we see? As I said, with the environment, storks and babies, that could be an effect, but we don't know for sure. So, what does a good scientist do? Asking more questions, exactly. We would, for example, ask the question, is there any data available that shows us that the environment somehow improved? Is it that the Swedes got miraculously more fertile? Could very well be that, that was the time when the first porn movies came up. That I got inspired, right? It's a little bit like, when does it come out, 50 Shades of Grey? No, I'm just general. So people are expecting a baby boom after that. Yeah? I have enough problems as well, yeah. So, the take-home message is, you should know about R values, about correlations. You should know how to do that on Excel. You can't do it in Google spreadsheets. Google spreadsheet doesn't have a good trendline function, but in Excel you can do that. Sorry? I can probably dig out a few statistics tests for you that you can look at for these things. Yeah? Yeah. And next week, next Friday, will be our last statistics lecture. No, don't worry. But in this lecture, we will look at clinical testing, because that is a topic that's shit hot and that people need to know about. So, I shall see you next week. Remember what I said about these correlations. Use them, but be careful what you're asking for.